Any last questions that we had from 5-1 yesterday? Which one are you looking at? $63. Find all solutions. Now, folks, when they mean all solutions, solutions to trig equations, there can be infinitely many solutions to a trig equation, especially when you look at sine, cosine, and tangent. They repeat after a certain amount of time, right? So that means there's going to be infinitely many solutions. There's going to be infinitely many times when sine or cosine is equal to 1. We just usually restrict it in between 0 and 2 pi, but here they want us to find all of them. Okay? So we're going to solve this as we normally would, but then all those values that we find, we're going to have to add to it some multiple of 2 pi or some multiple of 360. And that will include then all of the coterminal angles that behave in that same exact manner. So when we find our angles, we're then just going to add either a 2 pi times some constant k, or a 360 times some constant k as well. So looking at 63, they're telling us that cosine x equals 0.37. Now, 3700ths. Is 3700ths a special function value that we know for cosine? No, it's not a 1/2, it's not a radical 3 over 2, a radical 2 over 2, or a 0, or a 1. So it's not one of our special values. So in order to find what our angle x is equal to, we're going to have to take inverse cosine of 0.37. We're going to have to take inverse cosine of 0.37. And I guess before I jump the gun here and get too far ahead, where is cosine going to be positive? Quadrants 1 and quadrants 4 is where cosine is going to be positive. So I'm looking for two angles that will have a cosine of 0.37. So when I go into the calculator and do this, that will tell me my first quadrant angle. The calculator always gives you our reference angle. So I'm going to go ahead and do this in radian. If you guys would do it in degree, please, just so we can see the comparison of the two. So I'm going to check my mode. I am in radian. You guys please run it in degree. So I'm going to take inverse cosine of 0.37, and in radian, I get x equals roughly 1.19. You guys got what? Let's go to the nearest tenth, please. 68.3. So those are my quadrant 1 angles, but how do I apply that now into quadrant 4? How do you apply a reference into quadrant 4 if we're talking degrees? 360 minus, in radian it would be. So 2 pi minus 1.19. You guys are going to do 360 minus. Now do the full value that you got in. Don't do 68.3, but subtract off second answer. Okay, so I'm going to go 2 pi minus second answer. You guys are going to go 360 minus second answer. So I get 5.09. And what did you guys get to the nearest tenth again? 321.7? No, 291.7. Okay. So x can be equal to 1.19 plus any multiple of 2 pi, or 5.09 plus any multiple of 2 pi. That would be my answer in radian. In degrees, you would have told me x can equal what? 68.3 degrees plus any 360 times k, or 291.7 degrees plus what? Any 360 times k. Now that will include all of our coterminal angles that are the same as 68.3 and 291.7. Same thing over here. This includes all of the radian angles that are the same as 1.19 and 5.09. Okay? So up to this point right here, it's exactly the same. But now they want every single answer that would possibly work. So we've got to add all of our coterminal angles as well. Okay. All right, with 63? Good there? Dawson, did you find it finally?
Yeah.
27? Using basic identities, simplify it down ultimately to a basic trig function for 27. All right, looking at 27, what's indicated to me to do in 27? Distribute. Yeah, a multiplication here is kind of shown off to me here. So what is sine x times tangent x? Sine x tangent x. Okay, now, Will, I'm just going to ask, did you change everything first? And you're ultimately going to get the same answer. It's probably just going to be longer than what I've done here. Okay? Plus what? Sine x cot x. Okay. Now, I like to do my multiplication first because quite often when we multiply, I might have to multiply a trig function by itself. And whenever I multiply a trig function by itself, I'm going to get that trig function squared. And whenever I have squares, I might then potentially have Pythagorean identity. So I always do those indicated operations first before I change things back. I've done my indicated distribution. Is there any possibilities of Pythagorean identities yet, though? No, nothing's being squared up there. So now the next obvious step for me to do would be to go ahead and do what? Break everything back into sines and cosines. Well, sine already is, so that just stays sine x over 1. I might as well make this a fraction if everything else is going to become a fraction. But what's tangent x? Sine x over cosine x. Plus, again, a sine x over 1 times cosine x over sine x. Okay, so before I can do that addition, I've got to do the two multiplications. Well, multiplication is easier. I just multiply straight across. Or if I've got like terms, I can cancel them out. So what happens over on the left? Sine squared over cosine. Sine squared x over cosine x. Plus, what am I going to get over here? Just cosine x over 1, right? Good luck, okay. Well, now I can do the addition if I have what? And what would that common denominator be? So what does cosine x over 1 become? Cosine squared x over cosine x. So ultimately we get the what then? Sine squared x plus cosine squared x over cosine x. We keep our common denominator. This is my first step. This is my second step. This is my third step. This is my fourth step. And now what do we recognize? A potential Pythagorean. Why is there a potential Pythagorean? Sine squared plus cosine squared. We've got two trig functions squared being added together. This is the Pythagorean identity. This is what? 1 over cosine x, better known to us as secant x. Secant x. Okay. Now all this is going to be important to us today because today, and when we get into 5.2, we're going to be proving identities. They're going to want us to prove that this is equal to secant x. So if you remember from Algebra 2, what we did is we drew a vertical line down through here. And what did that vertical line mean to us? We couldn't cross sides. So we had to pick a side to work on. And we always picked a side where there was something for us to do. Is there really anything to do over here on the right? The one thing I could do is change secant to what? 1 over cosine. But there's a lot more indicated for me to do over here. So I work at this side, and I just work on simplifying expressions, which is what 5.1 is all about, simplifying expressions. I simplified that expression all the way down to get secant x. Do I now have common ground on both sides? Yep. So in 5.2 today here, I have now proven an identity. I've proven that this side is exactly the same as this side. So no matter what I put in for x, sine x times tangent x plus cotangent x is always going to be equal to secant x. Okay. All right, with 27, with the simplification of that one there. Where'd you get lost, if you don't mind me? So you changed everything in the beginning as well? Yeah, so when you change everything in the beginning, now you've got fractions and you're distributing to fractions and it's making it more involved. I always do the indicated operation first before I change to sines and cosines. But ultimately, if you're very careful, you're still going to get the same result. So, anything else then, folks? Cheyenne? 76, true and false question. The domain of validity for the identity sine theta equals tangent theta times cosine theta is the set of all real numbers. Justify your answer. How many say true? All real numbers. How many say true? Nobody says true. Everybody says it's false. You say it's true. It's going to work for all real numbers. Anybody else brave enough to give a guess here? How many say yes, all real numbers? Show of hands. Yes, all real numbers. No, not going to work. Okay, why? Very good, right? What is sine theta defined for? All real numbers. What is cosine defined for? All real numbers. Is tangent defined for all real numbers? No, tangent is not defined where? Where is tangent not defined? Our odd pi over 2's, right? So if we had theta being pi over 2, well, that's the sine of 90, the cosine of 90, and the tangent of 90, but tangent of 90 is what? That's not going to work. So is this going to work for all real numbers? No, it's not. It's not going to work specifically for what values? The odd pi over 2's.
I said should because if you broke tangent down,
it still becomes a fraction, though, and then that fraction is going to be undefined whenever the bottom will be.
Then you get sine equals sine.
But ultimately, though, as it starts out as it is tangent defined for everything, though? No. Okay. What you're doing is you're manipulating it and you're changing it into something else. But what's happened is you've lost that root. Okay, you've lost that root. So as it starts out, no, this is not defined here. Now, ultimately, yeah, when you do that little manipulation to it, you've changed it, and now it is sine equals sine, but it didn't start off being that, did it? Okay, it started off with that tangent in there. That tangent is not defined everywhere. Okay, so this one is false. This one is not going to work at the odd values of pi over 2. Okay? All right, with 76? Is there anything else, folks? Okay, this whole lesson then, 5.1, all of the simplifying expressions is vital to us. We've got to be comfortable simplifying these expressions down because now what we're going to do is go into identities. And we're going to have to prove trig identities, which means we're going to have to be simplifying expressions down. And hopefully when I simplify this side down, it's equal to whatever I have on the other side. And then I've proven the identity. But again, we've done this before. We've talked about identities here late last week. What is an identity? What's an identity? Thank you. It's an equation that is always true no matter what you put in for the variable. X plus x is always going to be equal to 2x versus 2x plus 4 equals 8. That's only going to work for certain conditions. Identities are always true no matter what you plug in. And what we're going to be doing here is then proving that one side of the equation is equal to the second side of the equation. Well, obviously what's involved in this? Being able to simplify terms down. So all of this stuff here is stuff that we would have done in section 1. Cotangent x minus tangent x. What would you do here? Cosine over sine minus sine over cosine. You then would have found a what? Common denominator. Subtracted those together. Same thing here. All of these. Find a common denominator, add them together as a single fraction. That's very important. And then determining if these are equivalent or not. So this is a good exercise to prove if these are identities. Is the natural log of x squared equal to negative 2 natural log x? Okay. What are we allowed to do with exponents when we have log? We're allowed to bring them out front, right? So natural log of x squared could really be written as 2 natural log x. Is 2 natural log x equal to negative 2 natural log x? No. So is this an identity? No, that one's not an identity. But how about this one? How about the square root of x squared equal to x? Is this an identity? What does, and again here, are we looking at all square roots or are we just looking at one square root? Just one. We're just concerned with the primary square root here. What would they have shown if they wanted both? They would have shown a plus minus. Is this an identity? No. That is not an identity. But without those is an identity. Because the square root does what to the square? The primary square root of x squared is x, and x equals x. Yes, that is an identity, but this one up here is not an identity. Okay, you don't bring out a negative 2, we just bring out the positive 2. Okay, so how do you prove identities? To prove identities, we draw a line down through the equal sign. We can't work on both sides at the same time. We simplify the one side and hope that it ends up being the other. And if it does, we have an identity. Got an identity down here. If it doesn't, then we don't have an identity. Ultimately, can we work on both sides? Yes, we just can't bring terms from side to side. We've got to simplify this expression, and if necessary, we can simplify this expression. We're looking for common ground. Okay? And we're going to use our basic identities in order to do that. Okay, so general strategy, and this is exactly what we've done. The proof begins with the expression on one side of the identity. It ends with the expression on the other. Okay. In between, we're going to show a sequence of simplifications of expressions until we get to that one side. Let's get to an example. Always start with the more complicated side. If no other move suggests itself, convert everything to sines and cosines. Perform indicated operations, so on and so forth. Here we go. And let me get this to a separate sheet. All right, so here's the identity that we're trying to prove. So I start by drawing a line down through the equal sign, meaning that I cannot what? I cannot cross, and I've got to work on simplifying an expression down. Okay? But this one is one that really doesn't lend itself to seeing much. Is there really any operation that's indicated on either side for me to look at? No, there's not, is there? There's really not much going on in this one. What we're going to do here is we're going to multiply this by 1. What does multiplying by 1 do? Multiplying by 1 does absolutely nothing. But 1 has many forms. 1 is anything divided by itself, right? Well, take a look at my goal here. I start with this, but what do I want to have in the numerator? So I'm going to multiply it by 1. I'm going to take my sine x over 1 minus cosine x, and I'm going to multiply it by 1. It's just, what is that form of 1 going to be? 1, what do I want to have up top? 1 plus, I want to have 1 plus cosine x up on top. So I'm going to multiply it by 1 plus cosine x over 1 plus cosine x. Look at your goal, Dawson. What do I want to have in my numerator? So that's what I'm going to multiply by. Okay, completely legitimate move. I'm multiplying by what? Which does absolutely nothing. But what does it give me now? It gives me that 1 plus cosine x up in the numerator. And in my denominator, I now have 1 plus cosine x times 1 minus cosine x. Okay, so this was my first step. This was my second step. There's now something that's indicated for me to do here, and in the numerator it's kind of indicating for me that I could go ahead and do what? But I'm not going to distribute because I'm in hopes that what's going to happen? I'm in hopes that this sine x is going to cancel because what am I allowed to have in the top? Just the 1 plus cosine x. So I'm not going to distribute the top because I'm hoping in the bottom I'm going to get a factor of sine x that'll cancel with this. I am going to do the distribution in the bottom, and this is very importantly a what? A FOIL, and I'm foiling conjugate, so it's really just first and last, right? So I get sine x times 1 plus cosine x over what? One minus cosine squared x. What happened to the inner and the outer terms? They canceled out. There's a red flag blaring out at me right now. Possible Pythagorean identity, right? Why is there a potential Pythagorean identity here? 1 plus or minus a trig function squared. And what is 1 minus cosine squared? That's sine squared. So I have sine x times 1 plus cosine x, and I recognize the Pythagorean substitution here. This is sine squared x. I've got it now. I have a factor of sine x up in the top, and I really have two individual factors of sine x in the bottom. What's going to happen? The sine x up top is going to cancel one of the sine x's in the bottom, leaving me with 1 plus cosine x over sine x. The proof starts with the expression on one side of the equation. The proof ends with the expression on the other side. Is this the expression that's on the other side? Absolutely is, isn't it? Have I proven this identity? I have now proven this identity. The proof starts with an expression on one side, and it ends with showing what we get on the other side. And I have done that step by step. I have shown every step in the process of working our way down here. And again, this looks very much like your geometry proofs, doesn't it? Yeah, we've got what we start with up on top, and then we've got our statements and reasons. Well, here's all the steps we've done to prove I have what I have on the other side. Okay, so this is a not a geometric, but a trigonometric proof, or an algebraic proof, just with trig involved in it. So we start with the one side. We do whatever we do to get to what we get on the other side. Now, folks, this is a common first step. All I did was multiply by what? 1. But 1 has many forms to it. It can be anything over itself. Well, as I look at this one, there's not much for me to do. I can't change sine. I can't change cosine. But as I look at the goal, I realize that I need to have my numerator have a 1 plus cosine x. Well, how can I make a 1 plus cosine x over here? Well, if I multiply by 1 plus cosine x over 1 plus cosine x, which is multiplying by 1, which does absolutely nothing.
Could you just try to get a common denominator?
No, because if you're trying to get a common denominator, you work on both sides at the same time, aren't you? We're only allowed to work on one side. Could I have started with the other side? I absolutely could have started with the other side. Watch what happens if I work with the other side. Over here, I see I've got a sine x in the bottom, but I really want a sine x up on the top. So I'm again going to multiply by 1, which in this case is going to be the sine x over sine x. And so I'm going to get sine x times 1 plus cosine x over sine squared x, right? And I think, okay, well, we can cancel the sine x's out. Yeah, but what happens if you do that? You're right back where you started, right? Well, sine squared. I know that sine squared is equivalent to 1 minus cosine squared, right? And I recognize that 1 minus cosine squared, 1 and cosine squared are both perfect what? They're both perfect squares. Can I factor difference of 2 squares there? Yep, so sine x, 1 plus cosine x. What are the 2 factors of 1 minus cosine squared? 1 minus cosine x and 1 plus cosine x. Now can I cancel? And what cancels out? The 1 pluses, right? And leaves me with sine x over 1 minus cosine x. And is that exactly what I have on the other side? Yep. So could I have worked on either side with this one? Yes. Okay, it's just there's no operations or anything that are indicated to me in this one. And if you ever come across a case like that where there's nothing really indicated for you to do, multiply by 1. How do you determine what variation of 1 you're going to multiply by, though? Go over and look at your goal. Okay. I look over to the other side, and that's what I want it to be. Okay. Well, if I want to have a 1 plus cosine x in the top, then multiply by 1 plus cosine x over 1 plus cosine x. If I want to have a sine x up on the top, well, I'm going to multiply by a sine x over sine x. Multiplying by 1 does absolutely nothing. It just provides me with potentially a term that I want. Okay. All right with this proof? Either way? Okay, good. Let's take a look at another one. I guess we got to go to the homework to look at another. They seriously only provide you with 1 proof on here in the notes? Just 1 example, huh? Did I give you a set of thirds for 5.2? Here, they've got a lot more examples in the text. Okay. This is example number 2 from the text. Okay, so here's the identity that I'm trying to prove. So again, I start with a line down through the equal sign to tell me that I cannot do what? I can't use both sides. I'm going to work on one side and try to simplify it down to the other. Now, does it matter which side I start with? No, I'm going to start with the side that has more for me to do. Okay, so if I look on the left, what would I have to be doing on the left? Adding, right? Versus on the right, I'm multiplying. Well, which operation involves more, the adding or multiplying? And especially when we look at these and determine they're going to become fractions. Adding has more to do. So let's see if we can make the left-hand side look like the right. Okay. What am I going to do with tangent x? Because I can't add it to cotangent x, but I can change it to what? So my first step, sine x over cosine x plus cosine x over sine x, right? Well, I can't add fractions unless we have a what? And what would that common denominator be? Cosine x, sine x. So does this one already have the cosine x? Yes, it just needs the sine x. So what would sine x times sine x be? sine squared x over, and my common denominator is now sine x cosine x. Plus, well, this side has the sine x, but it lacks the cosine x. So cosine times cosine would be cosine squared x. So that was my second step, finding the common denominator and then going ahead and adding them together. Okay. What do I recognize now? What is the top equal to? 1 over sine x cosine x. Well, that's only one term. And as I look on the right side, there's only one term as well, right? There's only one term as well. Okay, well, what is 1 over sine x? Cosecant x times, what is 1 over cosine x? Secant x. Is that what the other side has? Have I proven the identity? Yep, I started with the expression on one side. I ended with the expression that's on the other. And in between, I used identities to simplify down. Questions on that one? Could I have gone the other way on this one as well? Could I have started with the secant, cosecant, and worked at the tangent plus cotangent? Absolutely, I could have. Absolutely, I could have. Let's see if we can get one more. We'll try to determine algebraically here which one's going to work. Okay, so they want us to determine if 1 over secant x minus 1 plus 1 over secant x plus 1 is equal to which one of these two. Okay, so we're going to start with this. Plus 1 over secant x plus 1. And we'll determine which one it is equal to. What's indicated to me? Addition of fractions. I have to have a common denominator, right? So this side has the secant x minus 1, but it doesn't have? Okay, so what is 1 times secant x plus 1? Secant x plus 1. Plus, this side has the secant x plus 1, but it doesn't have the secant x minus 1. And what is 1 times secant x minus 1? Secant x minus 1. And our common denominator is now secant x plus 1 times secant x minus 1. Okay, so can I do the actual addition up top now? Yeah, what's secant x plus secant x? We've got 2 secant x, right? 2 secant x. 1 plus negative 1, they're going to knock each other out, right? Let's do the distribution in the bottom. What's secant x times secant x? Secant squared x. What's going to happen to the inner and the outer products? Y. They're conjugates. Minus 1. I've got a secant x up top. I've got a secant x at the bottom. I can cancel them out, right? No, very good. Why? We're attached on the bottom, right? But what should I be recognizing in the bottom? At least a possibility, right? Tangent squared plus 1 is equal to secant squared. So what is secant squared minus 1 equal to? Tangent squared. 2 secant x over tangent squared x. And now what can I do with my secant and my tangents? I can break them down, right? So this is going to be, secant is what? So 2 secant is going to be 2 over cosine x. 2 over cosine x. And what's tangent squared x going to be? Sine squared over, but we're going to multiply it, so we're going to multiply by the reciprocal. So cosine squared x.
May I have your attention, please? We have to do an announcement. This is just a reminder that the trap shooting team should be at the Conservation Club immediately after school today. Also, your picture will be taken for the newspaper at 4 o'clock. Attention National Honor Society members. We will be meeting in the Distance Learning Room tomorrow during activity period. Your attendance is expected. The Drama Club is in need of shoe boxes. If you have an empty one, you can donate. Please bring it to the chorus room. Following students, please report to the office. Zach Burrell, Lucas Wesley. Thank you for your attention.
Cotangent.
Would the following students please report to the guidance office? Jasmine Loomis.
And then 1 over sine x is
Caitlin McGee, Caleb Goodell, Jacinda Tolliger, Nathan
cosecant.
Cannon, and Josh Claus. Please report to the guidance office. Thank you.
To cotangent x cosecant x. Which one is it equivalent to then? Option number 1. Option number 1 is equal to. Okay, now they wanted you to match them graphically to see which one was equal to each other. Well, we did it algebraically. We found out that this is equal to 2 cot x cosecant x. And folks, right now we're just all using just those basic identities. Okay, what we're going to do tomorrow, and what I would strongly encourage you to do as you're starting your homework. What did we do last year with all of our identities? Yeah, we quizzed them, but what did we do? Cheyenne, what did you do with all your identities? What did you do with all the identities? No, what, just this year. You've just done it recently. You brought it in the 2 times you come in for help. Write them down on one separate sheet of paper so they're all right there for you. You're not flipping back through your notes. I would strongly suggest that you write yourself a reference sheet that has all of your identities on it right there. So you're just referring to this one thing as opposed to flipping through your notes to find them. Okay? Questions at all, folks? Okay, it's not due tomorrow, but we should definitely be getting a start on the 5.2 assignment. Set of thirds again, was it? Okay, so get a start on the 5.2 assignment. Potentially. The next calculator